So good morning. Thank you to organizers for opportunity to give me this talk today. And my name is Gabriel Wlazlowski, and I'm going to talk about response functions of the unitary Fermi gas extracted from Monte Carlo simulations. Results which I would like to present you were obtained in collaboration with Piotr Magierski, Aurel Bulgak, Joachim Drut, and Kenny Roche. And actually, two of my collaborators had a talk during these workshops, so my talk essentially extends their talks, and I will try to focus on subjects which were not covered in previous talks. Okay, so first of all, let me start by setting the notation and defining objects, which finally I would like to compute. So suppose that I have a Hamiltonian, which can be divided into two parts. One is H0. It's simply Hamiltonian defining my physical system, which I would like to study. And I have external perturbation, H1, which I'm going to apply to my system. So I assume that this external perturbation, it's some time-dependent Hamiltonian, which can be written in this generic form. It's external field, H, multiplied by some operator of conjugate dynamic variable. Okay, so that's my perturbation. And now I ask for some physical quantity represented by operator A. I ask for its time evolution of this quantity. Right? So what I do, I define the deviation of expectation value of this quantity from its equilibrium state. This brackets with 0 means that I take expectation value with respect to this Hamiltonian without external perturbation. Right? So for zero temperature formulation is expectation value over ground state. For finite temperature formulation is a thermal average. Now I assume that my external potential is weak. I can control it in principle. So to say something about the time evolution of my quantity, I can use a linear response theory. And this theory simply says me that there is a linear relation between my external field and the response of my system. And this function here, which defines response, I'm going to call a response function for some observable A with respect to perturbation B. Okay, so here's a formula given by linear response theory. So the problem here comes down to computation of some expectation value of commutator of two operators with respect to this Hamiltonian without perturbation. So that's the thing which I would like to do. Typically, we work in a momenta space. So if you take this formula for response and transform into Fourier space, you will get a very simple expression which simply says that my quantity A responses with the same frequency as my external perturbation. Okay, and this coefficient between field and response, it's something which we call generalized susceptibilities. So it can be connected with a spin susceptibility, for example, or by general susceptibilities, I also understand transport coefficients, conductivities, and things like this. In general, my operators A and B can have a position dependence. For example, you can stick their density operator. So my general expression, it's in general, my generalized susceptibility has a dependence on frequencies and also some wave vectors. And function defined here, it has a complex values, so you cannot directly relate this function with some physical quantities. You have to extract from this function physical quantities. For example, if you take a static limit, so frequency goes to 0, and long wave limit, so wave vector goes to 0, you recover static responses, which are real, and then you can connect the static responses with physical quantities.
So you're saying the expectation value on the left can't be measured?
Expectation value of?
The left side. So
Uh,
it can't be measured in general?
Well, in general, we can also try to measure it, yeah. But what we do, we try to extract this quantity, okay, using this, the formulas. So now what I need my physical system, which I would like to study. So I'm going to show you results for unitary Fermi gas, unpolarized system. So my equilibrium Hamiltonian has very simple form. It's a kinetic part for two species, spin up and spin down components. And then I have contact interaction. It's attractive interaction. So I explicitly write here minus. And it's unpolarized system. So I have one coupling constant which I have to fix. And what we do, we simply fix this coupling constants to reproduce correctly scattering length, which for unitarity point it should diverges. Right? So that's how we fix this coupling constant. And to satisfy the unitarity point, you also should set the effective range of your interaction equals 0, which in principle, if you use a kinetic interaction, this interaction it's interaction with very small effective range. So we assume that we satisfy this condition. However, because of cutoff in momenta space, which you use to regularize interaction, this effective range is non-zero. It has some finite value. So it's a source of some systematic errors in our approach. Yeah, and of course, it's well known that this is non-perturbative system. You're not going to get the right answers using some perturbative approaches. So that's why we need some non-per.
Can one determine exactly what the effective range is? For example, by calculating the scattering amplitude at finite momenta?
Yeah, sure. We know what's. We know what's the scat. What's the? You're asking for effective range, right? Yeah. So in our case, effective range, it's 4 by p cut, or is it correct? Or
I think pi.
yeah. Yeah, that's the expression. So if our what I did, if my cutoff goes to infinity, effective range is 0, but in our case it's finite. Okay. Okay. So let me go further. So the method which we are using to solve this problem, it's path integral Monte Carlo method. So we solve this problem at finite temperatures. So what we compute expectation values with respect to this H0 Hamiltonian for fixed temperature, beta is inverse of temperature, and fixed chemical potential. So we use a very standard formulation of path integral Monte Carlo. So I'm not going to give you details about this this method, just only few words what we do. So we place our system in cubic spatial lattice, and then we take this imaginary time propagator, we chunk it into some small pieces, and for each chunk, now this beta is divided by some number of small pieces. For each chunk, we apply Trotter-Suzuki decomposition, so we separate kinetic terms and interaction terms. And then for interaction term, we apply Hubbard-Stoyanovich transformation. We work with discrete type of Hubbard-Stoyanovich transformation. So in this way, we reduce our many-body problem to some sum or integral over one-body problems, right? And then we sample this integral over one-body problems using Metropolis importance sampling. And because this is this model is very similar to attractive Hubbard model, it's well known that there is no sign problem, so which is good. One problem less. So this is what actually. So this is expression for a response function. So that's the function which you would like to compute. So here you have this expectation value, which we would like to compute. And here's a problem which we encounter. It's following that this time dependence for these operators, it means that these operators are in Heisenberg picture, right? So you have to apply this operator, real-time evolution operator, which is a problem, right?
Maybe interacting picture, right? Because they evolve with the Fermi time.
Could you repeat maybe?
So it's interaction picture, no?
No, it's Heisenberg picture.
Well, but if the operator, I think in this way you are basically evolving the states with the perturbation and the operator with the Fermi time. So it should be the interacting picture. Because this is not the full Hamiltonian, it's just HD. Right?
It's the full Hamiltonian.
It's full Hamiltonian.
H naught is the full, it's H plus H1.
So this is a Hamiltonian of my equilibrium Hamiltonian, right?
I think we're arguing about words. This is, you agree it's correct. I agree it's correct.
No, it's
Yeah.
correct. No, I'm just saying that maybe it's the interacting.
Okay,
The
so
name
this
is
is
not
words.
Heisenberg is interacting picture, but anyway.
Okay, nevertheless, you have this real-time evolution here, okay, which is a problem for Monte Carlo simulations. We don't know how to perform these operations. So what we can do in Monte Carlo, we can instead of that compute some expectation values of this type. So instead of imaginary time evolution operator, you have instead of real-time evolution operators, you have imaginary time evolution operators. So this can be computed in quantum Monte Carlo. And this object I'm going to call correlator in imaginary time. Okay. So in special cases, one can very easily relate this imaginary time correlator with this response function. For example, it happens when your A operator commutes with your Hamiltonian. Then you can simply get rid of this time dependence in your operator, and you can reduce your problem simply to computation of expectation value of some operator without time dependence, right? And the example of such this quantity which satisfies this condition is, for example, static spin susceptibility. Right? So here's a definition of static spin susceptibility. So this quantity measures how easily you can polarize your system once you have a difference in your chemical potential for two species components, right? So this basically it's my A operator if you treat this as operators. So it measures the spin of the system, and of course, because my interaction doesn't change spin, it commutes with Hamiltonian. So you can very easily compute a static spin susceptibility using quantum Monte Carlo, and it's very reliable simulation. So here are our recent results for static spin susceptibility computed in this way. So points are our results for 3 different lattices. Blue it's 8 cube, then red is 8 cube, blue it's 10 cube, and green it's 12 cube, and also for 3 different densities. So we playing with different lattices and different densities, we can try to say something about extrapolation to thermodynamic and continuum limit. Line shows a prediction of Fermi liquid theory. This is theory where there is no superfluid phase. System is in normal phase. So for fluids in systems being in normal phase, the spin susceptibility just simply decreases as a function as the temperature increases. On the horizontal axis, there's a temperature, okay, in units of Fermi energy. And in our simulations, we have some temperature where we see that we have a suppression of spin susceptibility, right? And this suppression we associate with appearance of Cooper pairs in our system, right? Once you have a Cooper pairs in our system, it's no longer too easy polarized system, just introducing small difference in chemical potentials, because first of all you have to break a Cooper pairs. So that's just for comparison, that's a prediction of BCS theory. So BCS theory predicts that this suppression in spin susceptibility takes place exactly for a critical temperature. Right? So if we compare our results where the suppression starts with critical temperature, which we can compute from finite size scaling analysis of condensate fraction. So this line shows critical temperature. Here it's located here. It agrees very well with other Monte Carlo predictions and with experimental value. So it's clear that in our case, the suppression starts somewhere above critical temperature. So this is a way how we confirmed our previous prediction that for this system, we have phenomena which is called pseudogap. Precisely, pseudogap regime is a regime of temperatures where you have Cooper pairs in your system, but there is no superfluidity. At the same time, there's no long-range order between particles. Yeah.
So TC is the result of finite size scaling.
Right.
And then for these finite systems, the change starts earlier at higher temperature.
That's true. That's what we expect. So this is, yeah.
Is there a way to, I guess you show 3 different sizes. How to distinguish this from finite size effects?
Finite size effects.
To identify a pseudogap from finite size.
Well, so in our case, we don't see any systematic trends in this result, so we cannot extrapolate in continuum limit. So we think that it's pretty stable if you change lattice sizes and densities.
So the A12, the point there with the 3 different colors is to show that A10, 12.
Yeah.
The results are basically the same.
Yeah. Unfortunately, we don't have experimental results which we could compare with our predictions. We have only one point generated by Keterle's group, so this is this point.
I guess what I'm wondering is the finite size correction, how much of a correction is that to these data points in terms of TC?
Where we did estimation for systematic errors, and the systematic errors we estimated that there are in somewhere between 10 to 15%. So even if you move this by systematic corrections, you are still.
It's not quite the same, the answer. If you calculate the critical temperature where the condensate goes to 0 in a finite system, for example, for A, it would be around
Okay.
0.2, or even a little bit higher. So the correction, finite size correction, it's significant. That's what you meant.
Finite size correction for critical temperature.
Yeah.
Okay. Okay. I thought that for this temperature.
It'll be basically on the upper end. Yeah.
Okay.
So it's significant.
Okay. So this quantity was easy, but typically it's not so easy to relate this imaginary time correlator with your response function. What we need to do, we need to perform an analytic continuation of our correlator. We have to do it numerically. So of the imaginary time to real times, or in practice we do to this continuation to real frequencies. And in practice, this problem comes down to solving some integral equation of this generic form. So here I have correlators, so points which are provided by my quantum Monte Carlo simulations. So I have finite set of these points, and these points are affected by statistical noise. Then I have some kernel function, which is analytic function. For given problem, it's given function. And then I have some response function which I would like to extract solving this equation. So it's unknown in this equation. So I'm going to call this response function as object, in sense that this is object for reconstruction from Monte Carlo signal. Yeah. And typically people say that this problem it's post problem, which is true. It is post problem. However, in case of quantum Monte Carlo approaches, we have two separate problems. One, that it is ill post, but second, that this problem is numerically conditioned. So I'll try to define for you precisely these two terms. Right? First term arises from the fact that we have a finite set of points, and this produces this ill-post. And the second problem is related that we have a statistical noise in our signal. So that's two issues. So first of all, ill-post linear inverse problem. So I have my integral equation. Because I have finite set of these points, I can write a discretized version of my integral equation. Right? So now this y, I are points which are fixed. So I can treat this kernel function of function only on one variable. Right? So what I have from Monte Carlo, I have overlaps of my kernel functions with my unknown object, which I would like to reconstruct. And now, in principle, you can treat it as some matrix, which in one dimension, it's labeled by I. So it's in this dimension, it's has a size of number of points, which I have in imaginary time. And in other direction, it's labeled by X. So it's infinite size in this direction. So I can apply SVD decomposition to this kernel matrix. And by means of SVD decomposition, you can prove that your solution can be divided into two parts. One, it's called projected part or normal solution. So this is part of your solution which is sufficient to exactly reproduce your signal coming from your points. And then you have another part, perpendicular part, which is orthogonal to your kernel function. So you can stick here whatever you want, and in this way you can generate infinite set of solutions for this problem. So that's the definition of ill-post problem. So in practice, it means that data coming from Monte Carlo allows you only to reconstruct this part of your object. So here's a very simple example how it works. So suppose that I have this type of equation to solve. This is a kernel which we have in case of extracting from Monte Carlo simulation spectral function. So that's a kernel. That's my unknown function. And here I have these G points. So what I do in this artificial problem, I create some artificial spectral function, A. So this is this blue line. Then I stick it here. I compute these integrals for some number of points fixed. Beta is a parameter which is fixed to be 10. And then having these points, I invert this equation and I extract my solution. Precisely what I extract this projected part of my solution. Right? So this is this red curve. So it's clear that if you have some small number of points, there is a significant difference between the original function. And if you increase number of points in imaginary time, you have better and better description of your solution, right? So that's the first requirement for the quantum Monte Carlo simulations, that in principle you have to produce a lot of points. You cannot just have a few of them, 5 or 10. In principle, you have to produce a lot of these points to get something which is reasonable. So we can construct two strategies of solving our problem. First strategy is very simple, just to generate a lot of points in imaginary time and assume that your projected solution is a very good approximation of your true solution. And this method works very well in case if you don't have a statistical noise for your problem. For example, in case of unitary Fermi gas, people use some approximate theory to extract response function. For example, T-matrix theory. So what they do, they just generate a lot of points in imaginary time. They compute them with machine precision, so they don't have statistical noise, and they simply invert this equation, and they have very, very good approximation of true function. However, in quantum Monte Carlo problems, we think that the better approach is second one, which assumes that since we cannot extract full solution, we should supply to our problem some a priori information, and using this a priori information we can try to improve our reconstruction ability, just somehow fixing this unknown part of our solution. And types of a priori information which we can provide to our problems are, for example, some rules, which in many cases we can derive. We can provide some constraints for our response functions, like typically there are positive, or we can say something about values of this response function in some intervals. And finally, what we can also do, we can propose some models, so at least we can say what we should expect qualitatively for our solution. Okay. And second problem which we have with this equation is that it's numerically ill-conditioned. So here's a solution of SVD solution for this my projected part of true solution. So the formula is very easy. What you do, you take your kernel matrix, you do a SVD decomposition. So you have singular functions. These singular functions are orthogonal to each other, so you can use them to expand your solution in this basis. And then you need the coefficients of expansions. And coefficients of expansions are given by a product of singular vector times your quantum Monte Carlo signal divided by singular value. Okay. And now, because signal is affected by some noise, by some errors, it implies that you also have some errors for these coefficients if you compute them. That's the formula for the error of computation of these coefficients. And now if you sort your singular values in descending order, that's lambda 1 is the biggest one, and then there's smaller and smaller and smaller, you see that if you decrease the value of your singular value, it amplifies your error of determination of expansion coefficients. So practically it means that in our projected solution there exist directions which are invisible for us due to statistical error, right? So in practical problems, the problem is that these singular values, they decay exponentially, so they decay very fast. So you can only extract some subset, reliable subset of this expansion coefficients. So what we do, we just divide this projected solution into two parts. One is this visible part, where you have these coefficients extracted with good accuracy. And the second is invisible part, and we combine this invisible part with this unknown part, coming from the fact that problem is ill-posed. So in our case, this unknown part can be quite significant, okay? And we have to fix them using somehow a priori information.
Your lambdas are always positive?
Yeah, by the definition, they are positive. There are singular values. So to solve this problem, what we use in practice maximum entropy method. So this is in practice it's very simple method. So what we do, we take our object which we would like to reconstruct. We assume that it's localized in some interval from A to B. We create a mesh for this interval, so we divide this interval into some points and its number of points. So to have a very good approximation of this object, this n should be very large. Okay. Typically, it's larger than number of imaginary time points. So if we discretize our solution, then we can write it as a sum. This integral equation we can write as simply sum. So this is some set of algebraic equations, and this aj are unknown in these equations. And what in practice we do, we minimize some functional, and this functional consists of two parts. One is chi-square statistics. So having some solution, we stick it here, and we predict values for correlators, and we check how well we reproduce quantum Monte Carlo signals. So these are points from Monte Carlo, and this sigma are uncertainties of determination of Monte Carlo points. So if you only use this term, the problem is ill-posed. I mean, there is infinite number of solutions. His square statistics is 0, and you have infinite number of solutions. So that's why we need some second term to make the problem well-posed, which is called the entropy term. So this is some function which depends on my solution and also on some a priori model which I should provide. So it's penalty term. It has a maximal value 0 if my A is equal model. Otherwise, it's negative. So it favorizes solutions which are similar to my model. And you have some parameter alpha, which governs the contributions between first term and second term. So you have to choose it very carefully. So this method has very strong foundations in statistics, and on statistics grounds you can prove that minimalization of this problem in principle leads you to finding the most probable solution A under some assumption that your solution is a model M-like. So that's the weakness of this method, that here you have some assumptions. You have to provide something to extract something, okay? Okay, in practice what we do, we minimize this functional, but we minimized it with some external constraints, so it's constraint minimalization. The first constraint comes from SVD solution, so we impose that once we have a solution and when we project it, we should obtain this visible part by SVD method. So that's one constraint which we provide. So in this way, we make that we have two methods which are, and we produce solution which is correct in these two cases. It's a solution of two methods at the same time. And moreover, we supply here also as a constraint some rules if we have, or some asymptotic tails if we know. So whatever we have about our solution, we provide it here as constraints. So we found that these external constraints greatly improves the ability of our reconstruction. So for unitary Fermi gas, we are lucky because we have a rather significant amount of exact results. For example, because of Shinatan works, for many response functions we know tail asymptotics, which typically are given by contact. So contact sits there, and we know how it behaves in high frequencies. We also know a lot of some rules which are exact results. In many cases, they also contain this contact quantity. So we can provide here a significant amount of a priori information to improve the reconstruction ability of this problem. Yeah. And to decrease the influence of our model for finite results, we use a strategy which we call self-consistent maximum entropy method. So precisely what we do, we don't assume one specific model, but we create a class of models which are parameterized by some parameters. So it's some vector of parameters f. Right? In standard maximum entropy method, what you do, you fix this value and you solve for one given model. What we do, we start with some model. We solve our problem. So we minimize this functional. Having solution, we update our model. So we fit these parameters in this way to maximize overlap between our model and solution. And since we have new model, we have new functional, so we again minimize it, and we repeat this procedure until convergence. Okay, so we found that this method has this advantage that it's very weakly sensitive with respect to initial values of these parameters which we choose. It's still sensitive with respect to class of models, but it's very weakly sensitive to these initial parameters. Okay. So I'm going to show you one example. So this is it's not artificial example, it's a true example. It's a real example of vector reconstruction of spectral function of our system. So what here's a class of models which we provided. So we assume that our solution is something like a sum of two Gaussians. So here, as a 3 parameters which describe my class of models, I have a position of mean value of my Gaussian function, standard deviation, and amplitude of Gaussian function. So I have 6 parameters. And in one case, we start iterations from solution which I have two Gaussians which overlap. So they are exactly the same two Gaussians. And in the second case, we start with Gaussians which are separated by some distance, right? And this is the black curve, it's solution. So that's a typical picture which we see that whatever we stick at for the first iteration, we converge to typically to the same solution, finally. Okay, however, it is well known that this method sometimes fails. Okay, so it's known for a long time. And typical situations where this method fails are following. So if you have some sharp structure in your response function, like a delta function or something like this, typically what happens, this method, we simply overlook the structure. So this plot, what happens, this blue curve, this is what you have from reconstruction. You can overlook some sharp structures or some tiny structures. Other possibility is that if you have sharp structure, you can reconstruct it, but improperly, in this sense that, for example, sharp structure are reconstructed as some wide structures. So width of the structure, it's reconstructed improperly. Or the last situation which we found, and it's also well known that it exists in these problems, is that if you have two structures which are too close each other, so there is some critical distance between two structures, then you do not resolve them as two structures, but you simply reconstruct it as one single structure, something which is average over these two structures. So these are problems which you can find in this approach. However, there is one hint for unitary Fermi gas. Typically, these sharp structures which cause problems are related with quasi-particles. And at least for unitary Fermi gas, at low temperatures, we do not expect to have a well-defined quasi-particle. So maybe we might be lucky, and there is no sharp structures in our spectral function for this particular system. Okay, so that's the hint that it might work in practice. So I would like to show you two applications of this method, and both of them are extraction of transport coefficients. So first application is extraction of spin conductivity. It's very simple quantity. Let us define the spin current. So it's a difference between currents from spin up and spin down components. Okay, and now we assume that we apply external force, weak external force, which couples with opposite signs to the two spin populations. So we drag one spin population in one direction and second spin population in opposite direction. And in this way, we create a spin current. So this spin conductivity is simple coefficient between your force and your spin current. Okay. And similar to spin susceptibility, we expect that this quantity is strongly affected by presence of Cooper pairs. When you have a Cooper pairs, you cannot so simply create a spin current, because first of all, you have to break your Cooper pairs. So when we enter in the regime where we have a Cooper pairs, we should observe that this is strongly suppressed by presence of Cooper pairs. So qualitatively, we can say something at least what to expect about this coefficient. So in practice, what we do, we compute the correlator, which is of spin current times spin current correlator. So we compute this quantity. So here's our integral equation, which you need to solve to extract. And what we extract here is a frequency-dependent spin conductivity. So to match it with this quantity, you have to take a static limit. Omega goes to 0. It's this static spin conductivity. And we have a constraint. We know that it's always positive. That's one constraint. And second constraint, we know how it decays for large frequencies. So it's given by contact, which we can extract just looking at how our momenta distribution tail decays. So we extract it and supply for this constraint, and we do maximum entropy method with this constraint. Yeah, so here are examples of this frequency-dependent spin conductivity. So here's a frequency spin conductivity. For two cases, this is for critical temperature, and this is 2 times critical temperature, so this is normal phase. Okay, we impose that this tail should be, that our solution should converge somewhere here to this tail, so around 10, right? But actually from reconstruction, this is reconstruction. From reconstruction, we see that our spin conductivity is very well described by tail asymptotics, even for very low frequencies, equal about 3 times Fermi energy, or even here 2 times Fermi energy. And it's not surprising. For example, we know from Monte Carlo simulations done by Joaquin, or also from experiments, that when you look for occupation probability, it also very fastly converges to asymptotic behavior. So, for example, for Fermi, for momenta is equal 2 times Fermi momenta, you have very good description by tail asymptotics. This is occupation probability times momenta to power 4. So this const value means that we converge to tail asymptotics. Okay, so if you simply translate this momenta using this very simple formula to frequencies, you actually match this value very good. So at least this part seems to be reconstructed good in a proper way. Okay. Yes?
Why it seems to start to deviate with large frequencies?
Here?
Yeah.
Well, this gray bounce shows errors of reconstruction. So this tail asymptotics, it's within error bar, okay? Then it goes.
What happens?
No, then it converges to, of course, to this to this tail, because here we have constraint imposed. Okay, so it smoothly converges to that. It's no divergence here that it goes like this. It's something like a small bump, right? But this tail is always within uncertainty of extraction. Yeah, and here for critical temperature, we clearly see that there is suppression of. So there is a hole here. It's suppression of spin conductivity, as we would expect. So if we take these 0 frequency values, which are static spin conductivities, here what I precisely plot the spin drag rate, which is essentially inverse of spin conductivity. So here I have a temperature in units of Fermi energy, spin drag rate. Okay, so that's the normal phase. It's pretty constant. And then at some point, for temperatures 0.2, 0.25, we see that it goes up, it blows up. So it means that spin conductivity is suppressed. Right? And when you match this point, when it happens with these very reliable predictions for spin conductivity, this temperature exactly matches with this region. So it seems absolutely correct to be absolutely correct. I mean, absolutely consistent with spin susceptibility prediction. So that's another hint for us that we did everything correctly, right? At least we have a very, qualitatively, we have a correct picture. And second quantity, which I would like to comment shortly, is shear extraction of shear viscosity from quantum Monte Carlo. So standard definition of shear viscosity, it's a quantity which determines friction force per unit area created by shear flow. So that's the standard definition. Other definition which you can use, it's if you have an incompressible fluid or bulk viscosity, it's equal 0 for this fluid. This is a case of unitary Fermi gas. It was proved that bulk viscosity is 0 for this case because of scale invariance of the system. Then shear viscosity simply gives you rate of kinetic energy dissipation per unit time. So you have some flows in your system, and the kinetic energy of this flow decays with, it's converted into heat with rate given by shear viscosity. Okay. You can use a kinetic theory to compute the shear viscosity. It's very simple result. Of course, kinetic theory works only for a system in high temperatures, right, where we have essentially Boltzmann gas. So this theory says that shear viscosity is a product of density, average momenta of particles in your system, and mean free path of particle. And if you assume, it might be naive assumption, but if you assume that this formula qualitatively holds also in low temperature regime, what do you expect? That because mean free path of particles, it's very short. It's essentially the average distance between two particles, so it's shortest mean free path which you can produce in the system. You can expect that for strongly interacting systems like unitary Fermi gas, this shear viscosity should be extremely small. So you can expect that you have nearly ideal hydrodynamic behavior for these systems. And indeed, this is it was seen in experiments. So typically what people do in experiments, they take some gas, cloud of gas, then they remove a trap, and this cloud evolves in time, right? And then they try to describe time expansion of this cloud using a hydrodynamic, and they essentially find that they have a very good description of evolution of this cloud as a function of time using an ideal hydrodynamic without viscosity coefficients, which means that they are very, very small. Okay. The reason why people are very interested in this quantity is following. In 2005, Kofton, Son, and Starinets, they conjectured that based on string theory, they conjectured that there exists a lower bound for the ratio of shear viscosity of entropy density. So they conjectured that this ratio is always bigger than this constant. It's 1/4 pi. You have Planck constants and Boltzmann constant. And later it was found that this bound is valid for large class of string theories. Okay, so people started to think that maybe this is universal bound for this quantity. And indeed, we haven't found a fluid which violates this bound in nature. And moreover, this bound is saturated. And when this bound is saturated, people started to call these fluids as a perfect fluids. This bound is saturated in case of strongly coupled theory. So the string theory says that if you have strongly interacting systems, this ratio for this system should be very small. And indeed, this is what we see in experiments. We have two examples of strongly interacting fluids. One is quark-gluon plasma created in heavy ion collisions. So it's very hard to extract this coefficient from heavy ion collisions, but people try to do it. And it's very model dependent. So here's some recent report where it shows how this extraction for quark-gluon plasma evolves as a function of time. So now what they predict they have now two sources of experimental data. There are collisions at RIC, at Brookhaven, and at LHC. So they predict that this ratio is about 2 times or maybe 3 times above this hypothetical bound. Okay, and here units are chosen in this way that h bar and Boltzmann constant is equal 1. And this ratio was also measured in case of unitary Fermi gas. So here are results for trapped system. So this is system in the trap this is energy of the system, but this is essentially temperature. You can translate it to a temperature. So it's a temperature behavior, and in very low temperatures, it's pretty close. It's, let's say, about 4 times above this bound. Right. However, this is trapped average. So in trapped average, you have a cold center, let's say, and you have very hot edges. And these edges gives you a significant contribution to viscosity. So trapped average should be above values for uniform system. So uniform system, for uniform system, this coefficient it's below these experimental points. Okay, so we decided to compute this quantity in our Monte Carlo approach, because this is again transport coefficient It's very similar to computation of spin conductivity. So integral equation which you solve, it's the same. Here you provide a slightly different correlator. It's stress tensor type correlator. Again, we know a tail asymptotics, which is given by contact. And moreover, we have a sum rule, which gives you, once you integrate your spin conductivity, it gives you the result for this integration. So here are results of our extraction, of our first attempt to extract this coefficient for two lattices, 8 and 10. So there are two sets of points. And if you divide by this is shear viscosity over density. If you divide it by entropy density, here's the result for this ratio, which we see that it has some minimal value, slightly above critical temperature. Critical temperature is 0.15. So, and this minimal value it's about 0.2. So it's only 2 times higher than prediction of this hypothetical bound, right? So if we compare it with experimental results, they are below experimental results, so this is good. It should be like this. However, to say something if this is correct or not, this picture, it's actually what you should do. You should take our results and do average over your trap. So for example, using a local density approximation. And in this case, it's known that this procedure, it's very hard to do in practice. The problem is following, that in your cloud, you have, let's say, dense center. So center of the cloud you can describe as using hydrodynamic, but you have also edges which are very, very dilute. And from point of view of hydrodynamics, these edges are no longer fluid. Okay, so you cannot apply hydrodynamics to the edges. And if you do this, you simply get that this trapped shear viscosity is infinite. It leads you to divergence. So typically what people do, they divide your cloud into two parts. One which you can describe by hydrodynamics, second part which you can describe by kinetic theory. And they try to somehow match these two descriptions. Okay? But in this case, you have some parameters which are unknown, and in practice what they do, they simply fit to experimental points. So this is no longer a comparison with experimental. But what we can do very simple thing, and the simple thing is following. This green line, it's kinetic theory prediction. So what we see that our points, they pretty fast converge to kinetic theory prediction. So starting for temperature 0.4, we can say, well, our points are well described by kinetic theory prediction. Okay. So the simple thing which you can do, you can just remove this hydrodynamic part and just describe whole cloud by kinetic theory, and using kinetic theory make compute trap averaged value. There is no longer divergences in this case, and this is what you get actually. So this is a average shear viscosity as a function of temperature using only kinetic theory. So this line, it's a prediction of kinetic theory. Okay, forget about this dashed line. This solid line is a prediction of kinetic theory. So starting from 0.4, actually we see that it very nicely reproduces experimental points. So again, this part seems to be at least consistent with experimental points. However, we don't know nothing about this part. Okay, we don't know how to compare it with experiments. And what we found also is that this point which I showed you are results of shear viscosity under assumption of some class models. Okay, so we assumed some class of models, and then we solved this problem. However, you can change your class of models, and you can play with different classes. And this actually leads you to different values, typically higher than we found. So just by playing with different class of models, we found that you can find some class of models where you predict the higher values of shear viscosity or this ratio. But nevertheless, we produced some bound that whatever we do, we always are below this bounds. So this red curve gives our estimation for upper bound for shear viscosity and the ratio of shear viscosity to entropy density. And quite recently what we did, we did again simulations, but this time with bigger lattices. So we went up to 12 cube with lower densities to be closer to continuum limit. And with higher accuracy, we generated correlators with higher accuracy. Yes?
Typically, when you increase the size of the lattice, you keep the filling factor constant, or you fix the number of particles?
Typically, we fix number of particles. So our density is lower and lower. Okay. So filling factor, it's bigger lattice and smaller filling factor. This is what we do.
So in this case, we are actually looking at together at two possible systematic errors: the size of the lattice and the filling factor.
Yes. So we repeat our simulations with bigger boxes, bigger accuracy, and this is essentially what we get. So this is a set of points which are pretty scattered. So what we did some smooth approximation of these Monte Carlo points, while the scatter of these points were associated with errors of determination. Yeah, and again we found that actually what we recover our previous results. So these results, at least they seems to be stable. Okay. So I think that I stop here. So thank you very much for your attention. Yep.
The plot eta over S, with the higher temperatures deviate.
Eta over S.
Yeah.
This one?
Yeah. Eta over S at high temperatures. So did it start somehow to go away from this green line?
Well, yeah.
What is the reason?
I mean, it's not conclusive if it deviates or not, because the error bars are one standard deviation only, right? So with probability 67%, your error is with this bound, right?
Did you look at
So
points at higher temperature, or this is like one?
no, we stopped here. We don't have for higher temperatures points.
Related to the critical temperature, you mentioned that it was calculated by doing the finite size scaling with the condensate fraction. For condensate fraction, you mean quantity which you extract from the long-range behavior of the two-point correlation function, or was it the winding number giving superfluid fraction?
Yeah, two-body density matrix.
And what kind of finite size scaling should one use, and what is the critical exponent that will? Well, I guess it's difficult to extract it, but what do you assume for the values of the critical exponent?
Well, yes, the critical exponent was assumed. Critical exponents which are given for breaking of U1 symmetry, right? So, yeah.
Is there an idea why the minimum of this eta over S is above the critical temperature and maybe in the center of where you?
Well, so it's in these simulations it's slightly above critical temperature, right? But here, when we repeated the simulations, you have some bound, some errors, okay? And now the critical temperature it's within error, so it's not clear that it's at above critical temperature.
So is that yellow band still above KSS bound?
Yeah.
Or no?
Yeah. So this is KSS bound. Okay, so it actually touches it.
Yellow band.
I think
You didn't explain the yellow band. Huh?
Well, at this point it reflects scatter of data at Monte Carlo points, right? At low temperatures.
Low temperature is something else.
Yeah, at low temperatures there are predictions that the phonon there are predictions for phonon contributions for shear viscosity, and in our case, because of infrared momenta cutoff, we do not capture correctly phonon physics. So what we did this: we took this prediction of phonons and we simply created this yellow band to capture this phonon contributions also. Right? So that's why it diverges here. Yeah.
Questions? I remember that yesterday we sort of agreed that this was also the time for